Hello everyone, welcome to a new edition of the ANEMEL Webinar series. I am Leitat Flamarike, I'm part of the communication and dissemination team, and I will be your presenter for today's session. So ANEMEL, we are a European project. We are funded by the European Innovation Council, and we work toward the production of green hydrogen from seawater. So to do so, we are developing electrolysers while avoiding critical raw materials and fluorinated forever chemicals. I know that you might not be familiar with these terms. Don't worry, we have published two beautiful blog posts on our website, which is anemel.eu, and then you can go there and read them and learn more about this and why are we avoiding them. And also, I wanted to mention that this is already our 8th webinar. So in case you have missed our previous webinars, you can watch them all on our YouTube channel. So here. And well, it is a great pleasure to introduce our two speakers for today's session. So we have with us today Eleonora Crenna and David Wilde. Hello to you both. Hi, how are you?
Hi, Larry.
All good. And you?
Hi. So they are also part of ANEMEL as they work on the sustainability strategy within our project. And that's what they are going to explain to us today. How they are going to introduce the life cycle methodologies used in ANEMEL. So Eleonora, she is a senior research associate at the Institute of Energy and Environment at the University of Applied Sciences of Western Switzerland, and also life cycle assessment analyst, LCA analyst at the CIRAIG International Consortium. In ANEMEL, in our project, Eleonora is responsible for managing and performing the LCA of the novel electrolyser system. And also, she is as well as guiding the eco-design process. So that's Eleonora's duties. And on the other hand, David, he is a senior researcher in the sustainability area at Leitat Technological Center, based in Spain. And his work focuses more on sustainability assessment from a life cycle perspective across different European research projects related to advanced technologies, to the bioeconomy, food systems, as well as the circular economy. And within our project, he's more focused on the potential socioeconomic impacts and guides the development of more sustainability solutions. So, well, before we will start with Eleonora's presentation first. I want just a quick reminder for our audience that you can post your questions here in the chat. I don't know if it should appear here or here, and we will address them at the end of both presentations. So Eleonora, as I said, you are going first, so whenever you're ready, we are listening.
Sure, let me share my screen then.
Perfect.
So here we are, and we go into
I
presentation
can
mode.
see it. Perfect. I'm
Nice,
muting myself.
nice. So thank you, Leire, for the introduction, and welcome everyone to this webinar today, where you're going to learn about the sustainability methodologies that we use inside the ANEMEL project. So let's start from the environmental aspect of sustainability that involves life cycle assessment and eco-design. So in today's agenda, today, in this first part of the webinar, you will learn why it is important to assess the environmental sustainability of energy system and particularly of hydrogen technologies. You will learn what life cycle assessment and the eco-design approach are. And finally, you're going to see how we are using these methodologies in the ANEMEL project. So thinking about the energy system. So of course, what we all want is some energy which is clean, which is reliable, and which is also affordable. But there is a big question that we ask ourselves, that is, how do we know which technologies are actually sustainable? Because some emissions are obvious. I mean, if we think about the smoke that comes out of chimneys from industries, but some other emissions are more hidden. For example, those that are coming from mining of materials, because these are not really part of our everyday life. And this is where life cycle assessment, that is shortened as LCA, comes into hand. Indeed, LCA basically tells us the full story. This methodology reveals the potential environmental impacts of our energy systems. But what is actually LCA? So LCA is a standardized methodology that quantifies, so it gives a measurement of the potential environmental impacts of all the processes that are happening in the life cycle of a product. And when you say all processes, it means from the acquisition of resources up to the end of life, going through the manufacturing and the use phase. So LCA takes into account all the economic activities, so the processes that are associated to a product. And it also takes into account a comprehensive set of environmental impacts that cover aspects, for example, like ecosystem quality, biodiversity loss, human health, and also the use and the depletion of natural resources and water. So the LCA methodology is based on a standardized framework, which follow 4 iterative steps. And we are going to see all of them right now. So the first step is called goal and scope definition. And during this step, the LCA practitioner needs to ask some key questions. For example, why are we performing this life cycle assessment? What are we going to assess and how are we going to assess it? And finally, for whom are we going to do this analysis? So who is our target audience? So here on the left side of this, on the right side of the slides, you can see a simple example of a product system. And this example is kind of familiar to every one of us because it's a product system which has the function of serving a hot beverage, for example, coffee, during every day during the course of 1 year. And in this particular case, we have the particularity or the specificity of a coffee or hot beverage that is served in a ceramic cup. So if we think about the why is about the goal of our study. That means, for example, we want to quantify the environmental impacts of this system, and then we want to compare it to another system that provides the same function, but is using, let's say, a paper cup instead of a ceramic one. And in this way, through the analysis and through the results, we can make a choice on our daily habits, for example. If we think about the what refers to the definition of the scope. So it means the definition of the system itself that we are going to analyze. And it means defining which processes we want to include, which processes are relevant to include, and which one we are going to exclude depending on the goal that we just set. And if we think about the possible audience, Possible audience could be me, could be you, could be any person interested in understanding which are the potential environmental impacts of this daily coffee drinking using a ceramic mug or another kind of cup. Then, whoop. Yes. So the second phase is called lifecycle inventory, or as we abbreviate that as LSI. It's about the collection of quantitative information for each of the processes that we are included in the product system. And with inputs, so with quantitative information, we need all the amounts of materials that we need to input in the system and also that leave the system. So if we take the example of the production of the ceramic cup, that is one process in our entire system, this quantitative information means, for example, the amount of the color paint that we need, the amount of electricity or the heating that is consumed during the production of the cup, as well as the resources that we are taking from nature, like water and clay, and also all the emissions, so all the substances that we are emitting to the environment, like, for example, the amount of dust that is produced during this process. And finally, emissions also like waste, can be solid waste, can be wastewater. So this process of collecting information, collective data, collecting quantitative information is done for all the processes inside the system. And when it is not possible to collect the data from primary sources, so to collect data on the field, let's say, then we make use of databases that are specific LCA databases that have already inventories available. They are already compiled for various types of processes and also various regions of the world. The third phase is the impact assessment, and it's about the selection of impact assessment methods and the related indicator that will allow us to quantify the environmental impacts. There are different types of analysis and results that we can obtain doing an LCA. One, for example, is the computation of impact profiles. This is where the environmental impacts for the same indicators are shown and are compared between product systems. Another type of analysis, it's called contribution analysis. And this allows us to identify the main contributor to the overall environmental impact. And with main contributor, we mean the materials or the processes or even the life cycle stages that present the highest impact. And finally, we can have a scenario comparison. And this, we can do it by modifying few parameters within the product system to identify how relevant they are and what is their potential to reduce the overall environmental impact of the product system. And the final phase, that is the result interpretation, is basically about giving explanations of all of this analysis. So finding what is behind all of these results. So from the LCA, we move now to the eco-design approach. In simple words, eco-design is an approach that helps designing and developing a product, keeping in mind the environment, and particularly focusing on reducing the potential environmental impact of this product that we are analyzing through its overall life cycle. And this happens at an early stage of the design. So LCA and the eco-design approach are very well connected. LCA can be considered indeed as a tool for the eco-design because LCA provides the quantitative method that measures the inputs that then are taken into account into the eco-design approach. So in a simplified way, we can say that the eco-design approach follows three main steps. The first step is about performing the LCA and identify the so-called hotspots of impacts. So identify those contributors that I was mentioning before that represent the most of the impact along the life cycle. For example, in the graph that you can see on the right side of the slide, it's a very generic product system where the contribution of each life cycle stage is shown. So here we can see that the biggest bar is basically represented by the end of life. That means that the end of life carries the highest impact across the life cycle. And this is our focus in the eco-design. The second step is about identifying the key parameters, so understanding which are the specific aspects that are causing this higher impact. In the case of the end of life, can be, for example, the type of end of life treatment, it can be its efficiency, it can be the energy consumption, and so on and so forth. And here, it's very important to have exchanges with technical expert, because then we go into the third part, that is, with the help of the technical expert, the idea is to find feasible solutions that can improve the design to have a better environmental performance. When we follow the eco-design approach, we have to keep in mind two main principles, let's call them this way. The first principle is the life cycle approach. Because it is important to keep in mind that, well, first of all, it is important to have an overview of the overall life cycle of the product. And it's also important to keep in mind that once we make a new design of the product and we change it based on the first LCA results, it might be that we have a shift in the inputs. So in this example here, that is just a re-elaboration of the previous graph, the end of life was our focus. We managed to reduce the impacts of the end of life, for example, by improving the efficiency of the end of life treatment. But what we can see is that now the manufacturing becomes the main focus because it's getting more impact. So it's important to have this overview, this big perspective. The second principle is about the multi-indicator approach, meaning that we need to check results on all the environmental impact indicators. In this way, we make sure that the final results show improvements on all the environmental aspects, and we are not creating, let's say, extra negative impacts. One of the relevant tools that we use to perform the eco-design approach is the so-called eco-design strategy wheel. And this is very helpful when we want to brainstorm possible solutions to modify the design of a product with the technical expert. So the eco-design strategy wheel is a tool that presents 8 strategy areas, from the selection of low impact materials, the optimization of manufacturing technique, up to the optimization of the end of life system. And each of these areas represents opportunities to reduce the environmental impact. So now that you had an overview of these two tools or these two approaches that are related to the quantification and the assessment of the environmental sustainability, now the question is, why applying these tools to hydrogen? So hydrogen is very central nowadays in the decarbonization strategies, and many research projects are very active in this field. So as for any other technology, not just hydrogen, it is important that we avoid all the risks associated with greenwashing. This means that to be able to make environmental statements in favor of a product or a technology that are robust, we really need the support of proper and quantitative analysis. So how are we applying these methodologies to the ANEMEL project? Well, first of all, in the ANEMEL project, we performed the LCA of the entire value chain of hydrogen production, considering the anion exchange membrane electrolyser as our technology of reference. Through the LCA that we performed at different stages of the life cycle, we were able to identify the hotspots of the potential environmental impacts. For example, on the left side of the slide, you can see the environmental impacts associated to the overall hydrogen production system. And we can see how the blue bar that is referred to the electricity that is consumed during the operation of the electrolyser of the stack represent more than 90% of the overall impacts for all the indicators that we have analyzed. Then we decided to dig a little bit further into the system and also to try to understand in terms of the stack itself and its material, what was the main hotspot in this case. So on the right side, you can see the results related to the stack manufacturing. And we can see here then the end plates basically cover the biggest part of the overall impact of the stack manufacturing. So based on these results, we showed these results to our project partners. We organized a workshop with our ANEMEL partners, partners from both academia and from industry. And with them, we were able to identify the key parameters that are influencing such results and to also find possible solutions to improve the environmental performance of the hydrogen production system that we have considered in our study. So here I'm focusing only on two aspects, two main parameters that we selected. On the left side is about the durability of the stack, so the lifetime in terms of hours that the stack can operate. And on the right side is about the efficiency of the stack. So we modified this parameter going from 5,000 hours to 30,000 hours, keeping in mind that these numbers are, of course, very optimistic for this kind of technology that is still at an early stage, at a very, let's say, laboratory scale. And on the other side, we went from an efficiency of 60%, that is more or less the state of the art, to a better efficiency of 70%. And we could see how the results changed with an improvement for all the indicators, with a reduced impact for all the indicators. And based on all the ideas from the partners about the key parameters and the possible solution, we were then able to develop eco-design guidelines that basically support our partners in the next phases of designing and developing the new stack. So what is important in this project, and especially when we talk about LCA and eco-design, is the collaboration with industrial partners that have benefits on both sides. So by collaborating with industrial partners, we are able to co-design innovations that can integrate both the technical feasibility, so the possibility that this product actually will work in the real life, and the environmental considerations. And in turn, this basically allow the partners, industrial partners, to have products that have a reduced environmental footprint, that also increase the competitiveness of these products, because we are aware nowadays that also customers are really aware of the relevance of environmental sustainability. And it also helps to anticipate the regulation and, as mentioned, to meet customers' expectations. So to conclude, which are the important messages that you could take home today? So on the one side, we have LCA, we have life cycle assessment that measures the environmental performance of a product across the entire life cycle. And on the other side, we have eco-design that relies on LCA, and it helps improve the environmental performance of the product, starting from the very early stage of the design. And by applying these two approaches together, then we are able to design and develop hydrogen systems that are environmentally more sustainable.
Perfect. Thank you so much, Eleonora, for a very nice presentation. Just a quick reminder to our audience, you can post your questions in the chat here, still don't know where it is. And then at the end of the session, after David's presentation, we will address your questions. So now it's time to move on to the socioeconomic assessment work that we do in ANEMEL. And as we mentioned in the introduction, that's David's role. So I'm sure that we are looking forward to discover more about this. So David, whenever you're ready, you can share your screen and we are all listening.
Yeah. Hi, everyone. Thanks for having me. And thanks, Eleonora, for this great introduction on the first part of this today's webinar. I will be continuing right where Eleonora left off, talking about the socioeconomic assessment in general, but also, of course, in relation to the project of ANEMEL. So what will we cover in this second part of the presentation will be, first of all, diving a little bit into the question of why do we actually need socioeconomic assessments in hydrogen technologies. I will also provide a general brief intro into socioeconomic sustainability assessment methodologies, and also give you a brief overview of how we will implement these approaches specifically in ANEMEL. So why do we need socioeconomic assessments? So there's some thoughts that could come up among many others. So for example, one could think that renewable hydrogen needs to become cost efficient at scale, obviously, but it also needs to be competitive versus the status quo in order to have a chance in the market. One could consider that focusing only on economic and environmental performance may hide trade-offs, important trade-offs with the social dimension. Or, for example, that for funding or regulatory approval of hydrogen projects, they should not only consider environmental, but also they may also need social and socioeconomic credentials. As well as one could consider that socioeconomic assessment actually helps to anticipate as well as mitigate risks, for example, inequity, displacement, marginalization, but also that it ensures that benefits are distributed fairly and equally. These types of assessments, they can also be one response to a growing need for more meaningful and effective stakeholder involvement and engagement. And obviously, without understanding socioeconomic factors, hydrogen projects, especially new technologies, they may overlook things or even violate issues such as labor or social norms, which can lead to social conflict and reduced legitimacy. And obviously, nobody wants that in their project. Without going into actual regulation affairs, so here I just wanted to give a brief introduction into what may be relevant European level or global policies that could be considered in this context. So, of course, we have the European Union Hydrogen Strategy published in 2020, which, among many other things, on the technical and environmental level, asks for a cost-competitive renewable hydrogen. It also talks about that this should represent a just transition and be non-discriminatory, even though I have to say that concerning these last points that are more of a social nature, this is very much discussed in passing and superficially. So there's maybe also a limitation or something that could be improved for the future. However, on the European level, we also have something that's called European Pillars of Social Rights, which the European Commission committed to officially in 2017. You can see this is a broad range of social aspects that are concluded here that are considered social rights of European citizens. And of course, any project, any activity that is being pursued should respect these aspects. And on the global level, I imagine that you're very familiar with this. We have the United Nations Sustainable Development Goals, and here specifically, there's some goals that are very relevant to the hydrogen context, like Goal 7 on affordable and clean energy, but also goals such as industry, innovation, infrastructure, among many others. And of course, the objective of any project, of any new initiative, should be to contribute to the achievement of these goals, or at least do not impede the achievement of them. So moving on, what do we actually mean by socioeconomic sustainability assessments? So I really like this visualization of it because it makes it very clear what I'm talking about. So of course you have the technological pillar. This is the technology. It needs to work. It needs to be developed. And we have already heard from Eleonora about the environmental sphere, the environmental impacts, but also we have the economic and the social sphere. And only at the meeting point of all these aspects, when all of them are considered duly and work out, can we talk about a truly sustainable system. There's different methodologies that can be used to assess this. We've already had the introduction into life cycle assessment for the environmental dimension. In the economic sphere, we have life cycle costing, cost-benefit analysis, techno-economic analysis. In terms of the social, there's social LCA, product social impact assessment, and also social return on investment. And there's other methodologies that depend a little bit on the scope of the project and what's being assessed. We have also already heard from Eleonora about this idea of life cycle thinking, which is crucial, which is important, meaning the consideration of all life cycle stages, from the sourcing of raw materials to the manufacture, use, up to the end of life, which may also then include recycling, reuse, repair, etc. And there are specific methodologies here that respond to this, that are aligned with this, as we've heard, the life cycle assessment, but also life cycle costing and social life cycle assessment. And these three together form something that is called life cycle sustainability assessment. So that's a framework that is holistically capturing these three methodologies specifically and can serve as a framework for assessing the sustainability of product systems. So looking a little bit more closely at life cycle costing specifically, this in very general terms can be defined as an approach that assesses all costs associated with the life cycle of a product that are directly covered by one or more actors in the product life cycle. It's a definition by an organization called CIRAIG from 2008, and I highlight it here directly because it's important to consider that only costs incurred directly by one or more actors are being considered here. And the objective, again, in general terms, could be categorized or could be said to be to identify options with the lowest long-term economic burden and to support cost-effective and economically sustainable decisions. There's some key guidances here that are being published, starting with the CETAC Environmental Lifecycle Costing Guide from 2008, and there's an updated version that came out on this in 2011, a code of practice. Those are sort of the standard literature in this regard, but there are also some international standards. For example, there's an ISO standard from 2017 regarding buildings and constructed assets that has a chapter on life cycle costing. And of course, the ISOs that were also already mentioned by Eleonora from the 1440 and 44 from 2006 on LCA are very, very relevant here and serve as a reference. In general, we can differentiate between three different types of life cycle costing. For example, there's conventional life cycle costing, which, like I already said, covers internal costs that are borne by a single actor. So this could be the product manufacturer or the product user or consumer. Of course, it covers, in this case, then only the life cycle stages that are relevant to this single actor. So, for example, if you're the producer and you are not responsible or expected to assume any end-of-life cycle costs or have any obligations in terms of the use of your product, then these stages effectively do not need to be considered, which represents a limitation. But this is what's covered here. So, as objective, one could say that it's to minimize total cost of ownership or to maximize the economic efficiency. Next, we have environmental life cycle costing, which covers the same as the conventional life cycle costing, but takes a more comprehensive perspective, a multi-actor perspective. So here we do consider all actors that are involved in the life cycle of the product on the value chain, including the manufacturer, the one that's actually using the product, as well as actors that are involved in the end-of-life stages. but it also incorporates what is called environmental externalities. I wrote here some because there's some debate on this. So basically what this means is that environmental impacts that the LCA, for example, intends to discover in terms of emissions, toxicity, climate change emissions, etc., they can be monetized, or you can try to monetize them. It's complicated, but there are methodologies to do this. On some hand, they're saying we here only those should be considered that can be expected to internalized by actors within the value chain. So if the producer has to pay for emissions, for example, to buy certain certificates or some, for example, for greenhouse gas emissions, then there would be this would be considered. On the other hand, there's the opinion that all externalities should be considered, even if they consider actors that are not directly involved, which could be the local community that is affected by emissions or society as a whole. But overall, the objective would be to provide a more consistent basis for decision making that here specifically combines with the environmental LCA and also the social life cycle assessment. And lastly, we have something that's called societal LCC, which again builds on the two previous ones, but also includes social externalities, which is the same as environmental externalities, but on the social sphere. So potential social impacts that could be assumed by, for example, a local community surrounding a production site or society as a whole would also be attempted to be monetized here and considered. That's why there's no limitation to the stakeholders. So here explicitly all external stakeholders can be considered, and there's also no time limit. So even if you stop producing this or the product is at its end of life and disappears, let's say from the value chain, you can still consider the impact if they're long lasting, even from a generational perspective, if that's relevant. So the objective here is to capture the true total cost to society. Moving on to social life cycle assessment, or SLCA. So this, in very general terms, could be described as a methodology to assess the social impacts of products and services across their life cycle. This is the United Nations Environmental Programme definition from the guide from 2020. The objective could be defined as the identification of social hotspots and value chains, but also to inform decision making and support improvements in product systems, and ultimately the well-being of stakeholders. And I highlighted this because this aspect of stakeholders is crucial. I'll talk a little bit more about this soon. Here too, we have some key guidance documents. So the UNEP-CETAC guide from 2009, which was updated in 2020. Those are the guidelines for social LCA of products and organizations. They also come with a parallel publication of methodological sheets, which go into more detail on how to implement these indicators, etc. And also very recently published, we have an international standard, 1475, on the principles and framework for SLCA, which builds on the standard for LCA that Eleonora already introduced, and helps to set, let's say, a general foundation for how social LCA should be applied or should be enacted. And like I already said, it's closely linked and compatible with the methodology for life cycle assessment, with these 4 stages that were already introduced to us: the goal and scope definition, the life cycle inventory, life cycle impact assessment, and interpretation. So here you go through the same stages, ask the same questions, and it's very, very compatible and aligned with the LCA work. Yes, I already mentioned the importance of stakeholders, and I'll also talk about impact categories. So key comments here when you start out is, for example, who is affected. This is where these stakeholders come into play. Who is affected in this product system or in this value chain? Of course, you will also ask how they are affected. Here, the impact categories come into play. And to set more context, you also can ask, for example, where is this taking place and when? Here's just a visual overview from the UNEP-SETAC guide on stakeholder categories and impact categories. So concerning stakeholders, we can see these general categories, including workers, the local community, society as a whole, but obviously also consumers and value chain actors. And also the other categories are very broad. So whenever there's need or relevance, you obviously can define subcategories to further clarify what exactly you are talking about or focusing your assessment on. Then you have impact categories, again, very general, such as human rights, working conditions, health and safety issues, cultural heritage, governance, and socioeconomic repercussions. Important. So when we talk about stakeholders, we're not viewing them in this methodology just as passive recipients of impacts, but they actually have an active role when you embark on this type of assessment. So you try to engage them, you try to involve them as much as possible, because you want them to provide data and information themselves, to have direct data about their potential impacts and their views. And this is also is a clear form of stakeholder engagement, which can also promote social acceptance. Here, I just wanted to introduce briefly how these broad impact categories can be subdivided into subcategories. So again, here in this image, you see the stakeholder categories at the top. There's an additional one here, children, which was added in the latest guide. And then you have these subcategories that can be linked to each of these stakeholder groups. So for example, in the case of workers, we have subjects such as freedom of association and collective bargaining, child labor, fair salary, working hours, etc. And for society, we have things like contribution to economic development, but also corruption, poverty alleviation, etc. And obviously, it's always important to remember that all these subcategories and underlying indicators that can be used to evaluate the performance in these categories should be able to link to at least the socially focused United Nations Sustainable Development Goals. So now there's this visual here. It's a bit hard to see, but you can basically see how each of them has a place and can be linked to one of the Sustainable Development Goals, and therefore indicates that they're relevant to also allow an assessment of how the whole system that you're assessing is contributing on a broader level. So what about social impact assessment frameworks specifically for hydrogen technology? So in general, the identification and measuring of social impacts here is still on a relatively early stage, especially if you compare it with, let's say, publications or literature out there on the technological level, but also concerning environmental impacts. There's also a lot of diversity in terms of the methodologies that are being applied, what is being covered, the scope of assessments, which symbolizes a little bit a lack of homogenization in this regard. But very recently, we have newly published framework, it's called Conceptual Frameworks for Assessing and Monitoring Social Risks and Impacts Related to Hydrogen Technologies in their Value Chains from the GRC, that's the Joint Research Center, which is a sub-branch of the European Commission, which is extremely helpful in setting some groundwork, summarizing the work that's being done, and setting a little bit the stage for how this work could be performed in the context of hydrogen. For example, it separates a little bit overarching aspects which relate to, for example, safety, affordability, supply chain risks, which link to social aspects such as resilience or justice. And then it also clarifies technology-specific aspects, which are very local, specific to the local context. You can also look at things on a global scale. And here it's also helps us to understand how these methodologies can be applied depending on where your technology is at. So, for example, we already discussed that in ANEMEL, we are at the earlier stage, let's call it technology readiness level, the TRL. So if you have a low readiness level, that means you're basically in the design phase or still a development phase. Maybe you work at the laboratory scale. And then when you move up this scale, then you go to pilots. And when you have a very high readiness level, you are basically ready to enter the market. And your assessment will change accordingly. At the beginning, you have very little information. hydrogen. The technology is not really implemented in a specific context, so you have not really any stakeholders that you can ask about their experienced impacts. So then you can do something that is an assessment that is more risk related, so assess potential risks that they could face. And once the technology progresses, you can adjust your assessment strategy accordingly. Yes, and importantly and very helpfully, this framework also defines a relevant set of stakeholders for the hydrogen context, and also a list of specific social aspects in indicators that could be seen as relevant. Obviously, this is flexible. One can always add or take away things that are relevant or not in a specific context. So moving on, how are we applying this in ANEMEL? Here we have a strategy. We're using the two components that are already introduced, life cycle costing, and for the social life cycle assessment, there is a limited, reduced form of it, which I here call social impact screening. Concerning the life cycle costing, we are taking an environmental LCC approach, which in order to align clearly with the environmental LCA performed by Eleonora, but because of the stage that ANEMEL is on in terms of the technology development, and also because we are not really exploring a use case scenario within the project, this will have a somewhat limited focus on the producer perspective. That means hydrogen production in a presumed geographical context. We also you will use the same reference unit or functional unit as will be taken for the environmental LCA, which will be 1 kilogram of hydrogen produced over the stack lifetime. And here, importantly, we also have the option and actually the need to model possible future scenarios. Why? Because if you consider, let's say, the cost of manufacturing equipment at the laboratory scale in a lab scenario or small scale scenario, this is not very representative of where you want to get to or where you need to get to with this technology. So here we can and will need to create some scenarios that are more representative of where we need and want to get to, in order that our results are a little bit more representative. Also we will consider potential externalities building on the LCA results. So any impacts that are identified there can be monetized and considered here as well. So basically, this is a summary of what will be covered here. So capital expenses, obviously, of setting up the facility and the system, the operating expenses, that's the OPEX. So running the system, as well as maintenance, potential repair, etc. But also the end of life phase will be considered. So then when you decommission the installation, taking things apart, potential waste disposal costs, etc. And as I already mentioned, the environmental externalities, which in this case are most likely going to be indirect costs that will be largely assumed by society as a whole. LCC Plus, we're adding also an additional indicator which has not directly anything to do with life cycle costing, which is the levelized cost of hydrogen. This is similar to the levelized cost of energy for those of you that are familiar with this from the energy production context. And here this refers to the average cost of producing hydrogen over the lifetime of a production facility expressed per unit of hydrogen. So in this case, euro per kilogram. Why is this important? So this is a fairly standardized and common indicator that is being used to basically compare production systems of hydrogen. Gives a simple insight into how expensive is it to produce 1 kilogram of hydrogen with my system versus the status quo or other alternatives. We don't have to reinvent the wheel here. There are existing calculators. For example, this one that is being provided by the European Hydrogen Observatory together with the Clean Hydrogen Partnership, which is quite established and provides basically a calculation of hydrogen production costs for low temperature water electrolysis. If we can set this up in different European countries, as well as Norway and the UK. You can select different energy sources, for example, grid versus renewable electricity. It provides a set of default values for each context, for each country, but you can obviously play around with these things and enter your specific values to get outcomes, results that are as correct as possible, as close as possible to what you're doing. The results look a little bit like this. So you have on the right a total number. So that's your total cost that you could expect for the production of 1 kilogram of hydrogen. And then you see the subdivision of the costs, which also allows you to identify a little bit the hotspots on where your problem zones are. So for example, your CAPEX, then you have the largest share comes from the cost for electricity that you need in order to run your system. But there are also other OPEX costs, as well as grid fees, taxes, and you can also add potential incomes in terms of subsidies and byproducts such as oxygen, if you manage to sell that and generate income somehow. In regard to the social impact screening, so that's the second assessment dimension. So here, the key question that we would ask in the context of ANEMEL is, what are the potential social risk hotspots that can be associated with the equipment supply chain? The steps that we are taking here is first we identify key input materials or components of our system. That could be, for example, elements such as nickel, cobalt, platinum, tantalum, or aluminium. Once we have this, we can identify the main or likely source of these things. Here again, some sort of upscaling and perspective can be applied to make this more realistic. With this data, we can then start to identify potential social risk hotspots using tools for social LCA. Those are databases that are available, and methodologies. They're called PSILCA and social hotspot database. They're kind of standardized and accepted tools, but because they work with generalized sector and country data, it's also important to still at least accompany this with a literature review, which allows you to support your findings, but also to dig a little bit more deeper and identify other potential issues that you may have missed with the previous step. And with all the results and the outcomes from this, we then should be able to formulate initial mitigation strategies to those identified risks. And this is basically where we want to go with ANEMEL for sure, but this can be pushed further. And if it's not happening in ANEMEL, then obviously we will do this in follow-up projects. So you can move on to generate, for example, a social risk profile on the cell and stack level. You can generate a social risk profile based on the functional unit that was already discussed. And this then allows you to enter into comparisons with other technologies, which is obviously something that we're extremely interested in, and form more solid conclusions on the overall social risk performance of this technology. And yeah, just to close off, just a few snippets from literature regarding this aspect, the social aspect. So, for example, after I found that a potential major social hotspot is related to the hydrogen production equipment manufacturers. So, analyzing their value chain, they found that most impacts are likely to be, or most risks are likely to be located there. And diving in a little bit more deeper, specifically the platinum, which is used as catalyst material very often, comes out as a very clear social hotspot material. And for example, in ANEMEL, we are trying to go platinum free, which can already be seen as from the outset as a mitigation strategy to this social risk. It was also found that upstream supply chain processes, for example, associated with mining and refining, contributes to over 90% of most social topics, especially relating to the materials sourced outside of the EU. A lot of these rare materials and critical materials are not sourced in the EU. They come from other countries, and some of them in very precarious social conditions, including child labor, labor exploitation, and many other issues that could be considered. So when you use these materials, you should be aware of those risks associated with the supply chains. And also that it was interesting that even the social performance worsens significantly if hydrogen is used in a different European country than where it is produced. Without remembering the details, I assume that when you start converting, for example, your hydrogen to liquid hydrogen, activities like storage and also transport become involved, then you add a whole other list of activities that each comes with their own set of risks that add to the profile. And yeah, so the key takeaways that I would like you to take away from this presentation would be, okay, socioeconomic assessments, they contribute to a more holistic sustainability perspective. Again, with this visualization that I showed in the beginning, and also that life cycle costing and social LCA are life cycle thinking assessments, methodologies that are complementing the environmental LCA methodology, but can also be enacted standalone. But I think their strength is when you do them together, and which allows you to identify trade-offs. So if you see that here something works well in one dimension, but maybe not so well in the other, then that's something that you considered, or maybe the goals obviously would be to achieve win-win situations where everybody's happy and you're making progress on the whole front equally. And yeah, thanks for listening. That's it. This is where I finish up, and I believe we're moving on to the Q&A session. So Leitat, please go ahead.
Thank you so much, David, and thanks, Eleonora, again. They were very interesting presentation. I think it was really very clearly explained. So congratulations to you both. Let's move now to our questions time. I think we don't have any questions yet from our audience, but no worries. I have many of them because it was really interesting, as I said. So this one goes first to Eleonora regarding the life cycle inventory. Where do you usually get the data for those to make those inventories? Are they open databases? Are they privately owned and you have to pay for access?
Yeah, so we have basically two main sources that we generally use. Of course, for the data where we can, we take the data from our partners, from the ANEMEL partners, the way they produce their catalysts and membranes and how they assemble the stack. But for the data more in the upstream value chain, for example, concerning the acquisition of raw material, their processing, and so on, we make use of LCA databases. We use specifically EcoInvent. That is a database that is, I guess it's basically the most known database that is used in the LCA community. And for that, a license is needed, actually.
Okay.
Yeah.
Okay. So it's not for everyone. You need to have that license and then you can just use it for your LCA analysis.
Yeah.
All right. Okay, perfect. Thank you. And also I was wondering regarding the functional reference unit that you mentioned, that MAG that you were mentioning. I know you are working with an animal with a specific size, and also David mentioned it, but we might not be able to translate it to a bigger size. I don't know if we have some kind of gaps here, some kind of troubles, and how did you manage this gap between the small functional unit and then the scale up electrolyzers that we are working towards too?
Yeah, so we use this so impacts per kilogram of hydrogen produced as a main functional unit, also for simplicity and to be able to align all the life cycle thinking methodologies that we use. Of course, we can scale it up to, I don't know, higher amounts of hydrogen produced. But what is most important is the scaling up of the system itself. So at the moment within the ANEMEL, we are working with system that is on a lab scale, so on a very low TRL, so technology readiness level. But what we can do is to do what David was mentioning, so a prospective assessment by scaling up the system to a hypothetical industrial scale. By making assumption, for example, assuming that instead of having a stack of 1 kilowatt power, we can have a stack of 20, 50, I don't know how many kilowatt power, and then assuming a proper balance of plant equipment and all of this. Of course, it's a lot of assumptions, but yeah, this is what the prospective assessment implies when you don't have the real product system already at the higher scale that you need.
Okay, thanks, David. I don't know if you want to add anything here.
No, that was great. Nothing to add.
As Eleonora mentioned,
Thank you.
Okay, perfect. And also, I know that I'm still addressing these questions to Eleonora. I will go to David later on. So I know you draw some preliminary recommendations to our between our partners, like longer durability. Actually, you mentioned durability on your presentation, or using materials with higher recycled content. But I know I'm recalling our previous webinar, which was on ionomer architectures, that maybe this is kind of difficult if we are maybe there might be some technical aspects that are incompatible with these objectives. I'm talking about recycling here, that if it was a paper that they wanted to put the ionomer inside the layers, so maybe at some point it was difficult to recover those materials. So
Yeah.
maybe here is like finding a balance between what will work better for our electrolyzers and what will be better to our environment, let's say like that.
Yeah, so basically, that's the reason why when we do the eco design, we need the technical experts to be there with us, because from the LCA perspective, so from the environmental impacts perspective, we can come up with a lot of suggestions of what can be improved, but it remains on the environmental perspective. So the technical partners are very relevant in that sense, because then they can pick these suggestions and they can tell us, okay, this is feasible, this we can implement, this actually we cannot implement. Just an example. So we were commenting on the fact that it is also maybe relevant to use less material. So, for example, reducing the thickness of certain layers. And some technical partners were commenting, yeah, but there's a limit. We cannot reduce below a certain thickness. So there's always a bit of a trade-off between how you can reduce the impact and then, but still keeping the operability operation of your stack, of your technology. So it's really like a collaboration. So
Yeah.
yeah.
And David, I guess something similar could be applied when it comes to social and economic impacts, even though the economic part could be a little more tricky because we want something cost effective, something competitive, a competitive technology that companies actually want to implement it. So maybe here it's a little bit more difficult.
Yeah, exactly. I mean, in general, partners or firms are quite aware of the cost dimension. So if you start working with a very expensive material, the red lights go on very, very quickly. In terms of the social aspects, the awareness is a little bit lower, let's say, or it's the lowest if you consider the 3 dimensions of sustainability. And here's a little bit our job to spot those risks and spot those issues, to make sure that where we identify elevated risks that we are aware, because you obviously, when you have a supply chain, you can adjust it. You can decide, I buy from this source, I buy from that source, I buy from this country. Here is also the link with the eco design and, for example, recycling, because if you achieve certain recycling, that means you do not need to supply as much of the virgin material at some point, which is another mitigation method in order to reduce your social impact profile, in a sense. So this issue of trade-offs and how all things interact is important, and I think our role is to bother the technical guys and keep them on their toes, and have them not forget that there are other things that are important. Apart from that, it needs to work. Obviously, it needs to work, but it also needs to represent something, an improvement from a sustainability perspective relative to what we have right now.
Okay, and I guess it's apart from bothering our colleagues, it's difficult as there are many variables, many things that you need to take into account at the same time, together with the technical part, because we need something that needs to work, but it needs to work in a sustainable way. So there are many things at the same time that we are taking into account. And and also, please go ahead.
Yeah, exactly. And this is sorry. And this is also something that comes from enters now into Eleonora's field, this idea of eco-design. Because if we wait to give them feedback until the very end, when everything is defined and set up, in some cases it might be too late to make changes, or will be too complicated or too costly and too complex to go back to the drawing board. So that's why it's so important that we accompany these projects from a sustainability perspective, and also the eco-design from the beginning to spot these improvement potentials and help them to mitigate and address potential issues already early on, because later it might be too late. Sorry.
It's okay. I think it's something similar to the scaling up, that we need to think about going big and when we are already working on the lab scale, because something that works at lab scale, it might not work at a bigger scale. So yeah, something similar. And also, David, you mentioned platinum as a material that we need to really be really careful, really try to avoid. We are avoiding it on ANEMEL, but I was also thinking about cobalt. Like, I think that's like the example that everyone might know as the social condition around destruction of that materials. They are, you already mentioned them, child labor, etc. So I don't know if there are any more critical raw materials that I mentioned also in the introduction that we need to be aware of. Something that is really important here.
Yeah, absolutely. So this is a little bit our job that we're doing right now, building on the inventories that are being gathered for the environmental LCA. We're slowly starting to get a clearer perspective of what is going to be used. We're still in the phase where different materials are tried, so we might not have the final setup yet. So we're waiting a little bit for things to clarify, but it already in some cases we can start to investigate and look into these things. Some things may not. Cobalt is an extreme case, right? You may use only very little. There might be mitigation strategies of recycling it or using recycled sources, so you do not need to go to these controversial supply chains from the Congo or something like this, where we heard about the horrendous labor conditions that are linked to the sourcing of this material. But there's other materials such as nickel, for example, and even more general materials such as aluminium have risks involved in their supply chain. So that's something that we can look into, we can compare. If the consortium still considers alternative, we can also compare the different options and at least give an additional perspective from the social view, also from the cost side, to say, okay, use this if you can.
Okay, perfect. Thank you, David. And we need to conclude here as we have been 1 hour already. So it's been really a pleasure to have you both, and thank you so much for participating. Also, thanks again to everyone at home that has joined us today. And I need to thank to the European Innovation Council for funding our project. And also, if you want to stay tuned to our latest updates, you can follow us on our social media channels. And also, as I said, we have the ANEMEL webpage, which is anemel.eu, where you can find all our latest news. And well, so we hope to see you soon all on the next edition of the ANEMEL webinar. And thank you so much. Bye bye.